Out in the open desert, a horned lizard is slow, flat, and highly vulnerable. When cornered by a much larger mammalian predator like a coyote, simply running away is rarely a viable option. Instead of fleeing, the lizard triggers a highly specialized internal mechanism. Muscles restrict the blood flow, leaving its head, causing systemic blood to rapidly pool and build intense pressure inside its ocular sinuses, right behind the eyes. When the pressure hits a critical threshold, a targeted stream of blood ruptures from the corner of the eye, spraying up to several feet directly into the predator's mouth. The predator's reaction is immediate and visceral. Coyotes and wildcats exhibit intense gagging, head shaking, and physical revulsion, dropping the lizard and backing away. In any other context, fresh blood is highly nutritious for a predator, a reward for the hunt rather than a cause for physical revulsion. The violent rejection indicates that the lizard's blood must contain a highly noxious chemical additive, but horned lizards do not possess venom glands. The source of the chemical deterrent lies in what the lizard eats. Their primary food source is the Pogonomyrmex harvester ant, an insect fiercely defended by biting mandibles and a highly toxic venomous sting. To safely consume these dangerous insects, the lizard relies on extreme anatomical adaptations. It uses rapid millisecond precision tongue strikes to capture the ant, swallowing it whole to bypass the chewing phase and avoid bites to the mouth. Internally specialized esophageal papillae secrete a thick mucus to completely envelop the live ant as it slides down the digestive tract. This coating immobilizes the insect, preventing it from stinging the stomach lining. By evolving physical tools to defeat the ant's defenses, the horned lizard secured exclusive access to an incredibly abundant food source across the arid desert. Researchers suspected a link between this dangerous diet and the blood-squirting defense. They designed an experiment to test if eating venomous ants continuously fuels the lizard's chemical weapon. In the lab, scientists took blood plasma from horned lizards and fractionated it, filtering the fluid strictly by its molecular weight to separate it into distinct chemical bands. This data shows the results of offering isolated fractions to mice. The red bar indicates drastically lower intake compared to other fractions, showing active repulsion. The repellent compound in this red fraction is a small peptide with a molecular weight between 800 and 1600. To confirm the ant venom was the source of this peptide, scientists performed a diet swapping experiment. They depraved blood-squirting lizards of harvester ants entirely, feeding them a strict diet of crickets for several weeks. This graph tracks predator consumption after the diet change. By days 7 and 8, the blue bars representing the cricket Federal Reserve plasma spikes significantly. Without ants in the diet, the lizard's blood lost its defensive potency. This evolutionary tree compares closely related horned lizard species. While P. cornutum evolved to eat venomous ants, species like P. platy rhinos evolved to consume crickets and non-venomous bugs. This chart compares the palatability of plasma from those two distinct species. The massive blue bars show that mice readily consume blood from the non-ant-eating species, but strongly avoid the ant-eater's blood in red. These experiments clarify the relationship. The lizard's specialized weapon is entirely dependent on its ability to keep hunting a single genus of ant, while poison dart frogs survive by absorbing stolen toxins whole and intact. The horned lizard follows a different metabolic strategy. Harvester ant venom consists of massive, heavy macromolecular enzymes. These molecules are far too large to be the tiny 800 to 1,600 molecular weight peptide, acting as the repellent in the lizard's blood. To survive the toxic meal, the lizard's body actively metabolizes the massive venom enzymes, snapping them apart into smaller pieces. Those resulting small peptide fragments drift into the circulating blood, turning the lizard's circulatory system into a pressurized chemical weapon. Biologists call this interconnected evolutionary cascade the Phrynosomus wheat. A dietary shift toward eating venomous ants drove anatomical adaptations for swallowing them, which subsequently provided the circulating chemicals needed for a blood-squirting defense. Winning the biological arms race against a tiny venomous insect perfectly equipped the lizard to survive encounters with massive mammalian predators. It is a demonstration of evolutionary reuse. By dismantling a predator's venom, the lizard turns a dangerous meal into a weapon fired right back at its own enemies.